All right. At the end of the last lecture, we did a demo on with a laser pointer and the sieves. Today, we're going to start talking about the theory behind what was happening in that demo. And so, we're going to first talk about what we call interference. So, real quickly though, we're entering this section on X-ray diffraction, and we want to know why. We want to know why we use what we use. So X-rays. Let's talk about X-rays first. So X-rays are electromagnetic radiation, and they have a given wavelength. As we can kind of see down here from the chart, you can see wavelength. And if we kind of go down the chart, we see radio, microwaves, infrared, visible, UV, and we see that we have soft and hard X-rays. And we see that the wavelength for these is, from 10 to the minus 8 to 10 to the minus 12 nanometer, or sorry, that's in meters. So that's in the order of nanometers and less than that, right? And so these wavelengths, as we find out, are similar to the spacing of crystals. So we see here that that's similar to a water molecule right here, right? So we use X-rays because when we interact X-rays with crystals, they're at the similar spacing of those crystal planes, and therefore this allows us to probe the atomic arrangement on the order of what we refer to as an angstrom, so 0.5 to 50 angstroms, and so angstrom is 10 to the 10 to the minus 10, so we're talking right here. And so that's why we use X-rays. They're similar in size to our crystal spacings. All right, so now let's consider the X-rays as a wave and see what happens to them. And we want to just go over some basic theories with diffraction. So diffraction is when it interacts with a material. And so we have a wave. Here it's called wave 3 and wave 4. And then we have a scattering event. So the scattering event is what's actually important to us. That's our material. So basically, an X-ray interacts with our material, and it can do that in a number of different ways. So as you may be aware, like when we're going to test something, we're not just going to have one X-ray. We're going to have many thousands, millions of X-rays. And so what we're going to look at here is just two of them, though. We have wave 3 and wave 4. And it's a classic sinusoidal wave with the wavelength lambda from peak to peak. The amplitude, from 0 up to the peak, is known as A, or amplitude. And so we're going to take these two waves, and initially, these waves are what we call in phase. So the peak here matches with the peak here, and the valley here matches with the valley here. So this is what we term in phase. So what we want to know is that if these two in-phase waves encounter our material, what happens to them, right? And so diffraction occurs. That's the general term here, but it can interact in two different ways, and this is going to be one of them. So in this case, after the scattering event, the wave 3, is in this way, so it appears the same as wave 3. However, wave 4 interacts with the material in such a way that it actually shifts the wave. So now you see that if we compare wave 3 and wave 4 after the event, we see that the peak here matches with the valley, and the valley here matches with the peak. So these are what we term out of phase. Because now, if we look at this, the sum of these waves, what we actually see, the sum of these two waves, if you sum these up, you'll see that it zeroes it out, right? And so there's basically nothing. And so this is what we refer to as destructive interference. So they interfere with our material in such a way that they are out of phase, and therefore the amplitudes cancel. And this is an example of the kind of perfect destructive, right? Where their peak matches the valley, and so they perfectly cancel out to be destructive interference. So this is the first of the way. However, the other way that can occur is when these two waves, so now we're calling them 1 and 2, when they interact, so they're in phase to start, when they interact with our material, they are basically unchanged. The wave 1 appears to be the same, wave 2 appears to be the same. So whatever happened to it, these waves came out of the material in phase still. So the peaks match up with the valleys and so forth. And so when these sum to what we see, they will double the amplitude. So the amplitudes effectively multiply by the number of waves that we see that constructively interfere. And so that's what we call it, constructive interference, when they're in phase, and so the amplitudes multiply. So this is the other way. So whatever happened during the scattering event, they're in phase. And so that's interference in a nutshell. We can either have constructive or destructive, and it's all a matter of whether they're in phase or out of phase. And I should mention here that this is constructive and this is destructive, but there are, as you can imagine, there can be cases where they're not exactly one or the other extreme. And so in those cases, you'll have a combination of those two effects. But these are kind of the extremes of destructive and constructive interference. And in the next section, what we're going to talk about is what's happening here. What in the scattering event would cause these waves to either be in phase like this or out of phase like this.